The darkness here is absolute, an abyss that swallows every photon, every stray thought, every law of physics we hold dear. We are right on the edge of the ultimate cosmic trap, a place where gravity has ceased to be a force of attraction and has become, instead, a boundary, a one-way door to nowhere. I want you to feel that chill, the vertigo of standing where space and time itself are twisted into an inescapable vortex. This is the black hole, the quintessential cosmic void. But let me tell you a secret, a profound contradiction at the heart of modern physics. Despite the name, despite the terrifying perfect darkness that defines its popular image, the most advanced science tells us that this object is a liar. It's not truly black. In fact, it has a temperature, a color, and it is slowly, infinitesimally slowly, fading away. Come with me. We are going to jump right into the heart of this paradox to understand why the greatest absorbers in the universe are also subtly emitters. The reason we call it a black hole, of course, is purely classical, based on the physics of general relativity. This is the physics of the event horizon. Imagine a spherical boundary, a point of no return. Once any particle, be it light, matter, or a fleeting neutrino, crosses this invisible threshold, its fate is sealed. It must fall toward the singularity, the infinitely dense point at the center. The escape velocity at the event horizon is the speed of light itself. Since nothing can travel faster than light, nothing can ever get out. It acts like a perfect black body in thermodynamics. It absorbs all radiation that hits it, reflecting none. This is the simple, powerful, and visually accurate reason for the name. But the universe, as always, is far stranger than our initial models allow. The first crack in this perfect classical darkness came in the early 1970s, not from observing a black hole, but from a thought experiment about its fundamental properties. In 1973, physicist Jacob Bekenstein proposed a radical idea. Black holes must possess entropy. Entropy, in simple terms, is a measure of disorder, or the amount of information required to describe a system. If a black hole devoured matter, say, a starship full of complex data, and had zero entropy, it would violate the second law of thermodynamics, which states that total entropy in the universe must always increase. Bekenstein suggested that a black hole's entropy was proportional to the area of its event horizon. This seemingly abstract mathematical connection carried a profound implication. If an object has entropy, it must, by the laws of thermodynamics, also have a temperature. And if an object has a temperature above absolute zero, or 0 Kelvin, it must radiate energy. A black hole, therefore, could not be perfectly black. This idea was initially met with skepticism, even from the man who would ultimately solidify the concept, Stephen Hawking. But in 1974, Hawking merged the principles of general relativity, the gravity, with quantum field theory, the subatomic weirdness, and proved Bekenstein correct. This brings us to our next station on this impossible voyage, the quantum foam that bubbles near the event horizon. This is where the true color of the black hole originates. The source of the black hole's color is an elegant and deeply strange process known as Hawking radiation. It is not light escaping from inside the event horizon. That is impossible. Instead, it is energy generated right at the boundary. The vacuum of space is not empty. It is a constant, frenetic soup of quantum fluctuations, where particle-antiparticle pairs, often called virtual particles, spontaneously pop into existence, exist for a fleeting moment, and then annihilate one another, disappearing back into the vacuum. When this quantum dance happens right on the event horizon, the immense gravitational field interferes. It is possible for one particle of the pair to fall into the black hole, while its partner escapes. Crucially, the particle that escapes carries away positive energy, while the particle that falls in carries away negative energy. By absorbing a negative energy particle, the black hole loses a tiny bit of its mass. This escaping positive energy particle is the Hawking radiation. It is thermal radiation, meaning it has a temperature and, theoretically, a color. Now, we must escalate the scale to understand just how faint this color is. The temperature of a black hole is inversely proportional to its mass. The more massive the black hole, the colder it is. Consider a stellar mass black hole, perhaps 10 times the mass of our Sun. Its Hawking temperature is almost unimaginably cold, in the realm of tens of nano-Kelvin, or less than 100 millionth of a degree above absolute zero. For perspective, the cosmic microwave background, CMB, the residual heat from the Big Bang that permeates all of space, is a balmy 2.7 Kelvin. The black hole is colder than the space surrounding it. This means that, for a massive black hole, it is currently absorbing far more energy from the CMB than it is emitting via Hawking radiation. It is, in fact, getting heavier and colder over time, not lighter and hotter. So, while it is theoretically not black, because it emits radiation, practically, for every black hole we have ever detected, it is functionally and visually a perfect black body. The name sticks because the heat it emits is drowned out by the noise of the universe itself. However, the story shifts dramatically when we consider the truly exotic end of the scale: primordial black holes. These hypothetical objects, perhaps formed in the first moments after the Big Bang, could be tiny, the mass of a small asteroid or even a mountain compressed into a subatomic space. These micro-black holes would be intensely hot. A black hole with the mass of a large mountain would have a temperature in the thousands of Kelvin, emitting high-energy X-rays and gamma rays. This is where the black hole truly becomes colored, a brilliant, blazing source of high-energy light. This is the ultimate mind-bending consequence of Hawking's 1974 discovery. Black holes must eventually evaporate. Because every particle of Hawking radiation carries away mass, the black hole shrinks. As it shrinks, its temperature increases, accelerating the radiation process. It's a runaway effect. If we take our 10 solar mass black hole, the one that is currently colder than the CMB, it would take an estimated 1067 years to completely evaporate, a timescale so vast it makes the current age of the universe look like a blink. But the tiny, mountain mass black hole? It would evaporate in the blink of a cosmic eye, perhaps 10 to 11 years, ending its life in a final massive burst of gamma radiation. It dies not in darkness, but in a final brilliant flash of color, the ultimate white light. We have reached the limit of our journey, the point of no return for the black hole itself, its final, explosive demise. This leads us to the final, most profound paradox that Hawking radiation introduced: the information paradox. If a black hole evaporates entirely, what happens to all the information, the quantum data, the history of every star and planet it consumed? Quantum mechanics dictates that information cannot be truly lost. It must be conserved. But Hawking radiation is thermal, meaning it's featureless. Like steam rising from water, it tells you nothing about the water's initial state. If the black hole disappears and the information is gone, physics breaks. This is the frontier of theoretical cosmology, where physicists like Hawking and his contemporaries spent decades debating whether the information is encoded back onto the radiation, perhaps stored holographically on the two-dimensional event horizon, or if the black hole leaves behind a tiny, remnant particle. we set out to explore the simple contradiction in a name. Why is a black hole not black? We found the answer in the marriage of the two great physics theories, relativity and quantum mechanics, and the resulting thermal glow, the Hawking radiation. The name black hole is a beautiful, intuitive description of its gravitational power and its visual appearance in the modern universe. But the reality is far more subtle. It is not an eternal void, but a cosmic clock, ticking down through eons, radiating a faint, cold color that whispers of its eventual fiery end. It is a thermodynamic engine, a quantum furnace, and the ultimate proof that in the cosmos, nothing is ever truly perfect, not even a perfect absorber of light.